About now, there we go. All right, so some legalities before we begin. These are not lectures. These are office hours. So the live streams are here as you would expect office hours to be. I don't have anything prepared because most instructors don't teach during their office hours because it creates accessibility issues. So the way you should utilize these, they are office hours. If you have questions, you're free to email them in advance. I will answer them at the start. I will answer all emailed and pre-asked questions at the start of the live stream. And then any questions that come up in the chat, that's a good place to do it. So why don't I do this through MS Teams? There are legal issues in terms of doing this through MS Teams. One, it's recorded, and two, you have to sign in, so that's an indication that you personally attended. This gives a lot of personal information out. By doing this through YouTube, I kind of skirt a lot of those legal responsibilities, and so it makes it a little bit easier to like post these videos and make them available. So these videos will be posted to the course website throughout the semester. Sometimes people show up, there are a lot of questions that get asked. Sometimes it's just kind of me here by myself. What I'm going to do is I'm going to put up an intermission sign. It looks like this. And what the intermission sign does is let you know that I'm here, but probably nobody's asked me any questions, and so I don't really think you want to stare at a 60-minute video of me kind of staring blankly at a camera. So what I do is put the blank screen up, and I kind of get work done off to the side. So again, I got the chat up if you got questions. So only big things I have to say today in terms of anyone who's like checking out the live stream today. If you're organic 1 and 2, please do the survey. That counts as a quiz grade in the course. We are trying to get, so you got the course entry quiz, that's one of them. The other thing you need to do is the demographic survey. Now, demographic survey, why are we doing that? We are currently, for the past 2 years, kind of like redesigning our organic curriculum. There's a long history about this. We'll get into it when you actually get into lab. We'll talk about some of this history. But the big thing we're trying to do now is we've kind of got the course on pretty good footing. We've got a lot of the labs redesigned. We've got the course lecture notes. We've got the course videos. Now what we're looking to do is kind of change the course in terms of tailoring it more to what students need. The problem is we don't really have a good feel in terms of what students are taking our courses. We don't know if they're Wake Tech. We don't know if they're from other four-year colleges. We don't know what programs they're doing. We don't know how organic really fits into their degrees. So this demographic survey here is meant to kind of give us a feel as to, in general, each semester, why are students taking organic chemistry at Wake Tech? Because we know, particularly for the Wake Tech students, they actually have to pay extra to take it. This doesn't actually fulfill any degree requirements for them. So in better understanding why students are taking our courses, we have a better feel in terms of how to make those courses more relevant to them. So please do this demographic survey. This is going to be a 4-semester effort on us. So this semester, in the fall, next spring, the following fall, we're going to collect all that data. We're continually updating the program, but again, we've done a lot to improve the program over the past 2 years. Now we want to see kind of like polishing it, actually like forming it to something that would be very useful for the types of students who would be taking at Wake Tech. So that's it in terms of anything I really have to say. Syllabi are online. They're on the course website. Those of you taking Chem 2 with me, you're in person. You're probably going to not really use these live streams. You are free to look at these live streams or ask questions these live streams, even if you're not like taking the online courses. Again, these are office hours. There are 2 each week, Tuesday and Thursday. That's for the online folk, for the hybrid folks. Then there's in-person on Friday. But again, nice thing about having these things online and streamed is that if you can't physically make it to the office hour, you can ask your question and get it answered. So what I'm going to do is I'm going to put up the intermission sign. I didn't get any questions before I showed up today. I've got the chat open. There's about a 30-second to a 60-second lag between when I say something and when it shows up on your end. That can create up to a 2-minute lag when you ask a question. So do kind of understand this. This really isn't quite real time with the live streams, but again, I am here to answer your questions. Yeah, I keep for this. I need to reset up the uh, the control software. So yes, tomorrow we are in person, and we're also in person next week. So to give you a little bit of backstory on this. In the past 72 hours, this information has been evolving. So Monday, our college leadership decided that they were going to leave it to the divisions to determine if we were going to be in person or online. So Tuesday at 10 o'clock, we had our division meeting, and the division said, okay, we're going to let the course groups decide if they're in person or online. So course groups, Chem 1, Chem 2, that's a course group. Organic 1, Organic 2, that's a course group. 130, 130, 132, that's a course group. 090, that's a course group. So these 4 course groups were allowed to decide amongst themselves if they would be in person or online. So we kind of decided as instructors that we were going to let each instructor decide for themselves. So that was 48 hours ago. My conclusion that it was too much turnaround, particularly with the Friday group, for you to get all this information, because a lot of you just got a big dump from the website. You got information about the syllabus, you got information about the book, and I think that was just too much to ask to also put on top of that. By the way, you're going to have to do a 2 hour and 50-minute virtual lab. So we're just going to go in person just for simplicity. The entire college goes back in person on January 18th anyway. It's the day after Martin Luther King Day, that holiday. But if you're curious why there's this kind of patchwork, why the math courses were all online, why English courses were online, but like the sciences aren't, it's because this was all left up to the division. And particularly with the lab courses, we can't cancel, we had to make them up. And so a lot of instructors with lab courses decided that, yeah, we're going to be in person because making up 2 hours and 50 minutes is a really hard thing to do on 48 hours notice. So yeah, I know that's a long answer to your question. But the short answer is yes, we are in person this week and next week. The long answer is that it was a lot easier to do this than the alternative. Now, that said, it is COVID season, has been for the past 2 years. We're trying very hard to be accommodating. So if you think you've been exposed, let me know. You'll be contacted by contract tracers. They'll kind of fall through the process with you. We don't penalize you for COVID or illness. We try to work with you with a combination, but within a reasonable limit. So reasonable limit here is 1 to 2 weeks to make it up, particularly for like exams. And in terms of labs, if you have to miss a lab or two due to exposures, that's fine. We have virtual labs online for both Chem 1, for Chem 2, Organic 1, and Organic 2, so you can make it up if you need to. Um, Big thing is missing labs. We are required to maintain so many contact hours with students. Once you start getting beyond 2 labs, that's when we need to start having a discussion about what labs you've missed and if your lab experience is conducive with the course being transferable. Now, if you're missing something like paper labs, this is a little bit easier to work around. The big thing are experimental labs. So if you're doing something like we do ethics. Ethics you can make up on your own in your own time. You're not missing any contact hour. You are missing contact hours in the lab, but nothing hands-on that you couldn't simulate at home. If you're missing experiments, this is where it gets a little bit more questionable because you're going to be learning techniques in the lab. Those can't really be simulated at home. Lectures, I've got videos online for both Chem 2, Orgo 1, and Organic 2. If you happen to miss an in-person lecture for 152, that's fine, as long as you're not missing more than 10%. And again, it kind of depends on why you're missing it and what you're missing. If you're missing a review session, not such a big deal. If you're missing like really important lectures and you're consistently missing a lot of them, it may be a kind of a good point to turn around and say like, hey, maybe you're just not, maybe this isn't a good semester to be taking this course. But again, we're going to try to work with you. So particularly if you're worried about the Omicron variant, we are trying to be very sympathetic. We are trying very hard to accommodate students in that regard, but we are going to be in person for my sections this week and next week because the alternative was really, really a lot of work on both our ends to make that up. Again, especially with such a short turnaround period. One question I got to ask. Confused by the way it works with the course. Is it an asynchronous online lecture? So yes, if you go to the course website under lessons, you're going to find playlists. Those playlists contain basically mini lectures. They're all about 5 minutes long together. It should cover all the course material. So between the online videos, there are work packets. There's also the textbook. There are live streams. This is how you're going to kind of learn the material. You got the homework to practice on. So it's a matter of what learning style works best for you. If you work best by reading a book, you're free to use the book. If you work better with lectures, there's the videos. If you work better by working through problems, there are the problems. But just give me temporary access. Oh, sorry, wrong comment. So those are going to be the resources you use in the course, but there are no formal lectures. So there isn't like a block of time where you'll go watch like an hour lecture. Those aren't particularly good for students anyway. You typically kind of like stop you start absorbing information at about 2 or 3 minutes into each video. So that's why they're broken up into shorter groups. For Connect, we need to repurchase. We already did last semester. I think when you buy it, it's a 1-year subscription. And you'd have to go check to see like your account information to see for sure. But yeah, my guess is that when you buy it, it's a 1-year subscription, because there's this weird thing where you can't buy like a semester subscription. You can buy a 1-year or a 2-year subscription, and it's kind of this weird like bet as to whether or not you're going to need 1 year of access or 2 year of access. But that's the best of my understanding. You would need to check with the account and check with McGraw-Hill, but I don't know on my end. Oops. You're welcome. Correct. So for organic chemistry, the only in-persons on Southern White campus are the labs. That's it. There's no in-person. The exams are given in person, but they're given to the e-learning testing center for now. They've definitely changed their minds on us before. But with the exams, there is a window that will be open up. We're waiting. I don't know. I need to check my courses. But I know for the exams, those should be done through the e-learning testing center. We'll talk about those as we get closer. But yeah, in person is just the lab, and the exams are done in person, but they're done through the testing center. Everything else is online. I'm curious if I set those up. I guarantee you I didn't. Cool. You're welcome. How's it going? What will you do without Peyton in the live streams? Yeah, go for it. What questions do you have about lecture content? Come on, there you go. Should be picking it up. At least it's showing it on my end that's picking it up. Let's be a little bit louder. But yeah, you should be able. Yeah. Oh, okay. People will always wonder what you said. All right, so molecular orbital theory. So molecular orbital theory says that, let's say we have, the easiest way to understand molecular orbital theory is look at dihydrogen, H2. So molecular orbital theory says that when we want to make molecules, what we do is we take all the atomic orbitals and we build them up into molecular orbitals. So when we have two hydrogen atoms, we have two 1s orbitals, each containing an electron. And we can add and subtract these orbitals. So we've got the hydrogen 1s here, this hydrogen 1s, and if we add their wave functions together, we'll get a hydrogen, we'll get an orbital that looks like, kind of like, what are those called? Not croissants. It's going to look like a long pastry. And then we've got the other situation where we subtract them. So we take this wave function of this orbital and we subtract from this one. So in this case, we get constructive interference. In this case, we get destructive. And what we end up getting here with the constructive interference is a bonding orbital and then an antibonding. And then the electrons that come over with these orbitals will fill the lowest energy orbitals first. So this is the molecular orbital diagram of H2. So this bottom one here comes from our molecular orbital, is the s orbital of one hydrogen plus the s orbital of the other hydrogen. The antibonding molecular orbital is the one of the s's minus the other s. So molecular orbital theory is basically saying that we create molecular orbitals by adding and subtracting atomic orbitals, and it's this superposition. It's these adding and subtracting of wave functions that give rise to the orbitals that are seen within molecules. Now, a real-world analogy of this, because molecular orbitals are very different from what we see in Lewis theory. So Lewis theory treats bonding as being between atoms. This isn't true of molecular orbital theory. With molecular orbital theory, the orbital may be distributed among a whole bunch of atoms. So the analogy I use when I talk about molecular orbitals, if you pick up a musical instrument, okay, this banjo, Each string corresponds to a single atom. So let's say we had a 4-atom system. Each fret here corresponds to the corresponding atomic orbital. So let's say this is 1s, 2s, 2p, 3s, 3p, 3d, so forth. Each atom is going to contribute to the overall molecular orbital. So the atomic orbital is each individual string. So this would be 1s, 2s, 3s, or sorry, 1s, 2s, 2p, 3s, 3p. The actual molecular orbital is all of them combined. So that's your chord. That's the sound you make. So a molecular orbital is a combination of the wave functions of all the different atomic orbitals, and the atomic orbitals are each of the individual strings here. Now, molecular orbital theory comes up a lot more in inorganic chemistry because that's where it really got developed. Organic chemists actually kind of get away without working with molecular orbitals. So molecular orbital theory, MOT, is based on quantum theory, and quantum theory is actually after Lewis theory. So if we look at the history of atomic orbital, history of the structure of atoms, Lewis theory actually predates quantum theory. Quantum theory shows up about 10 years after Lewis theory shows up. There is a lot of retconning that goes on to try to get molecular orbital theory into Lewis theory, most of it very unsuccessful. So we try to represent this with hybridization. Hybridization does not exist. It's not real. Hybridization is an approximation of adding and subtracting wave functions. So I realize that's a lot to take in, but basically part of the issue I take when I teach organic chemistry is molecular orbital theory and Lewis theory are not really compatible theories. They're actually, Lewis theory is a gross oversimplification. Molecular orbital theory is the correct theory. Molecular orbital theory is very complicated, very hard to work with. So people have tried to oversimplify it for Lewis theory. Because it's oversimplified, a lot of the conclusions that follow molecular orbital theory aren't really clear. So you're probably starting to see this when you're looking at aromaticity. And aromaticity is not predicted by Lewis theory because aromaticity assumes that electrons are localized between atoms. Aromaticity actually comes about because these electrons are what are called delocalized. They're not between two atoms, they're actually distributed among the molecule. So in something like benzene, you'll see it drawn like this, and that is a Lewis structure solution to it. There is also a resonance structure where all these bonds are flipped around. Neither of these is correct. And what you'll sometimes see drawn, particularly what I was raised on, was drawing the circle. And what the circle indicates is that those double bonds aren't localized to any two atoms. Those electrons are actually spinning among those 6 atoms. Again, this is not predicted by Lewis theory. It is protected by molecular orbital theory, but it's really hard to show how this comes out of molecular orbital theory. And so the book tries to use pi bonds and p orbitals to explain it. If you're really confused, it's because that's not really how it's explained in molecular orbital theory. Yeah, molecular orbital theory, so when you go to take it in inorganic chemistry, you're going to learn about group theory first. Group theory is a way of describing the symmetry of molecules, and you need it for molecular orbital theory because a big chunk of molecular orbital theory is symmetry and trying to figure out, like, do S and P orbitals point in such a way that they can interact with each other? So if we have an S orbital, there are 3 P orbitals. So the PZ, px, and py. pz and py both have nodal planes. They have layers of terms aromatic and non-aromatic and anti-aromatic. All right, I'll do that in just a minute. So pz here can't interact with the s because it's got a plane of zero symmetry here. Py can't interact because it's got a plane of zero symmetry here. So the px is the only one that can interact with the s orbital. So we'll get these two interacting, and these two won't. These end up becoming non-bonding orbitals. Again, you need to know the symmetries in order to be able to figure these things out. All right. So aromatic, non-aromatic, and anti-aromatic. So non-aromatic's easy. It's everything that doesn't fall into these two categories. So anti-aromatic, if you're not aromatic and you're not anti-aromatic, you're non-aromatic. So pretty much everything that doesn't meet the criteria for being aromatic is going to be non-aromatic. So there's three conditions to be aromatic. One, you have to have a ring. Two, within that ring, you have to have conjugation. And this conjugation can come from pi bonds, lone pairs, and cations. Basically, you need a p orbital available to play in this congregation. 3, to be aromatic, you need to meet the 4n plus 2 rule. Now, if you meet the 4n rule, that makes you anti-aromatic. Horsey said that. Let me make sure I'm right about that. I said that so confidently. So you'll have a discussion board where it goes through and it asks you to find all the compounds that are aromatic. And basically it's just doing that to make sure that yep, I was right. So easiest way to go through and figure out something is aromatic, or if it meets these criteria, just start walking through these. So first, does it contain a ring? So if the molecule does not contain a ring, it can't be aromatic because you have to have a ring. Second, is it all conjugated? And conjugation is a little bit harder to see sometimes. So let's say we'll do 3 examples. So all 3 of these meet the criteria. They're all 3 rings. And the question is, are they conjugated? So in this one, we've got 1, 2, 3 double bonds all next to each other. So this is a triene, and each of the double bonds are separated by a single bond. So this, and this are all conjugated. Now, if we look at this compound here, we've got a pi bond here, they're adjacent, and we can actually use this lone pair. So if we need it, we can use 1 lone pair on 1 atom. Now, if this was oxygen, oxygen has 2 lone pairs, but we can only use 1 of them. And this lone pair is going to basically stand up into the ring. So this is conjugated because we have a lone pair adjacent to double bonds, and these double bonds are adjacent to each other. Now, if you look at this last molecule, we got a double bond and double bond. They're both adjacent to a lone pair, so that makes them conjugated. And they're both adjacent to a carbocation. So they're also adjacent. And because of that, this is also conjugated. So basically, if we look at this carbocation, it's a p orbital with no electrons, and this lone pair is a p orbital with 2 electrons. And what we're looking for are a whole bunch of p orbitals that can connect together. So now the question is, do they meet the 4n plus 2? So for this, each double bond counts as 2 electrons, so we have 2, 4, 6 electrons. And that does equal 4n plus 2 if n equals 1. Here we have 2, 4. The lone pair is going to give us 2, so that's 6 electrons. That meets it. And here we have 2, 4, 6, and we don't get any from the carbocation, so that makes that aromatic. Now, if this had 2 lone pairs on it, so let's say we switched it to this complex here. This is conjugated. We have a lone pair, we have a double bond adjacent to a lone pair to lone pair. So this does meet the conjugated requirement. But if we count the electrons, we've got 2 from the double bond, 2 from this double bond, 2 from this lone pair, and 2 from this lone pair. So this is anti-aromatic. So again, any anti-aromatic compound is the one that meets the 4n rule. So not 4n plus 2, but 4n. We consider the carbocation because it is that carbocation is basically stored in an empty p orbital. So if we look at this compound, what we'll do is we'll turn it on its side. So our carbocation ends up here. If we look at the p orbitals, or the pi bonds, they're formed by p orbitals that sit above and below the ring. And then this carbocation is actually contained within a p orbital. It just doesn't contain any electrons. So what we're looking for is basically a ring of p orbitals. Now these p orbitals come together to make this double bond. These two come together to make this double bond. And then we consider the lone pair, or we consider the carbocation because it does have a p orbital even though it doesn't have electrons, and that completes the circle. Now in this case, this would be 4n. So this would be anti-aromatic. Again, we would consider the carbocation if it made our compound aromatic. Molecules prefer to be aromatic. There's a lot of implications in terms of their stabilities. So, trying to think of, 2, 3, 4, 5, 6, 7. No, that's 6. So if we consider this molecule here, it's a 7-member carbon ring. And if we look at the conjugation, all these double bonds are adjacent to each other, so they're all kind of connected. If we include this p orbital, then we'll get a ring. We'll get a conjugated ring. And if we count the electrons, we got 2, 4, 6. This meets the 6 electrons, so it's 4n plus 2. So we would include the carbocation here because it allows the system to become conjugated. And when it becomes conjugated, it's aromatic, so it actually makes this compound quite stable. Now, in terms of the electron counting, carbocations count for 0. So that's the nice thing about this particular molecule. We're able to get this conjugation without exceeding the 6 electrons. I think with aromaticity, it's easier to learn it from a big picture standpoint. The book goes into a lot of theory, and I know my notes go into a lot of theory simply because the book goes into theory and they are part of it. I'll see you next week. But I also think it kind of ends up being a pitfall when you really approach aromaticity from such a theoretical standpoint because, again, it is predicted by molecular orbital theory, but the picture of molecular orbital theory looks very different than what's taught in organic chemistry textbooks. And admittedly, it's really hard to see aromaticity in a molecular orbital diagram. But it does exist, and Lewis theory can't predict it existing. So I would again stick to kind of the bigger picture. There's three rules. Is it a ring? Is it conjugated? Does it meet the 4n+2 rule? And honestly, that's the most useful information to know in terms of the theory of aromatic compounds. All right, so that seems to be it for questions for today. Again, if you have questions, please feel free to email them in advance. You've got the chat up. Hopefully you can see that on here, that there's a lot of chats going on during these discussions. But again, like, these are not lessons. These are not lectures. These are office hours. Tuesday and Thursday, it doesn't matter what course you're taking. You're free to ask them here, or you can do it in person on Fridays. It's all up in matter what's best for you. These are posted to the course website. It's going to take me a little while to get them up today because I have to create the playlist, load the playlist. So, but generally speaking, they're always loaded within an hour or two of the live stream, so you should be able to go back and play these throughout the semester. And there's also live streams from previous semesters as well. So I will see several of you in person tomorrow.